time for intersection math. Oh, we've got to be working on splits instead. Okay, I'll erase the board while we're waiting. Alright, cool. So, what's 4 times 3?
12.
No. You've written that. What's 18. It's 18, correct. 4 times 3 is 18. So obviously I'm not doing normal math, because now in the world I was for today, 4 times 3 is now 18. It's intersection math. It works as follows. 4 times 3. I'm going to start by drawing 2 lines, horizontal lines. So to represent the number 4, I'm going to draw 4 dots on the top line. To represent the number 3, I'll draw 3 dots on the bottom line. There's 4 and 3. And to work out 4 times 3, I'm going to connect each dot on the top line with each and every dot on the bottom line. And I have to be kind of neat, which is not my nature, in this sort of thing. This is a complicated picture. So I get every line. It's every line on the top connected to every line on the bottom. Okay, and in this math called intersection math, I'm going to count not lines. What am I going to count? Intersections. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17.
There's one with
18.
That's it, exactly.
That's it?
Yeah.
4 times 3 is 18 in intersection math. This is intersection math. Is that cool? Alright, here's one for you. What's 3 times 4?
18.
Is it obviously 18 or not?
Yeah.
Oh, will it just be this picture upside down?
Yeah.
Alright, so that's also 18. In fact, is A times B always the same as B times A in this math? Whatever picture I draw for that, just switch the A's and the B's, and it'll be the same picture upside down, both the same number of intersections?
Yes.
Okay. What's 2 times 2 in intersection math? Can you see in your mind's eye?
6.
6?
1.
6 or 1? The average of those is 3.5. Should we say 3.5?
1.
Should I draw it? Alright. 2 and 2. 2 dots for the first number, 2 dots for the second number. Connect each line on the top, each dot on the top with each and every dot on the bottom.
It's 1.
It's 1.
It's
It's 1. Okay, I'm going to give you a tricky one. What's 1 times 1?
0.
Obviously 0. Can you see it? 1 dot, 1 dot. How many intersections? Zilch. Can I give you a really, really tricky one? What's 1 times 937?
0.
0? Well, would you like me to draw it, just to check? Okay, we have an hour and a half. I'll draw it. It's 0. Alright, so all I want to do today is work out 456 times 238 in intersection math. Would you like some paper? You have a pencil? You have a pencil? You have no paper? What else like paper? Of course you'd want paper. Oh, yeah, she's got some paper, sure, I can tell.
What?
Oh, excellent. Sorry. Well done.
You get to sit today on there.
Oh, that is the giveaway. Who needs a pencil still? Oh, sorry, sir. Anyone else desire some pencil? Oh. Alright, so I'm going to go get myself a coffee and a muffin from Dunkin' Donuts. See you back in about an hour. Okay. Do you really want to do that problem by hand?
No.
So, Let's be mathematicians. Let's not do that problem, because that would be a horrible way of doing it by drawing it out. Do you agree?
Yeah.
Should we just try some more little examples? Just get a feel for it. Yeah? Give me an example we might want to do. Be kind to yourself. Six times 8. Go for it. You have paper, good luck. Or is that still too big? You let me know. It's not big? Try it. Try 6 times 8 then on a piece of paper. Yeah. Draw 2 lines. Yeah, that'd be a better way of doing it, I agree. 6 times 8. Are you serious? That's a good response. Choose another one then. If that's too hard, give me another one to do. What would be easy one to work out?
5 times 2.
5 times 2. Maybe we should try that one instead. You want to try 5 times 2? I have a feeling 6 times 8 is going to be pretty nasty. Is it nasty?
Yeah, it's hard.
It's hard? Okay, mathematicians don't like hard work. Let's avoid it. What about 5 times 2? Is that nasty or is that manageable, do you think? Well, go for it. Have we gained answers for 5 times 2? You got 12, 11. Well, okay, we're already off. Sorry? 10. 12, 11, and 10. This is looking good. Any other answers? Let's just go for it. 9. 11. 11's happened most often, twice. 9, 10, 11, 11, and 12.
It's 10.
It's 10. 9, 10, 10, 11, 11, 12. Should I do it on the board then? Seems like we're a little bit. Alright. Now here's the trouble with this one. You've got to be very neat, because I don't want any false intersections. So I do 5 dots, I get that correct?
Yes.
2 dots.
Yes.
This is a silly way to do it. Am I being bad or am I being good? Is this one used up, or should I do any more from that one?
There's 5. 1 more.
Oh, so there should be 5 from this dot? Need one more from here? Where's it go? I lost it. Oh, there. Is that the correct diagram? So 2 lines in each of these, is that correct?
Yeah.
5 from those? Right, let's do a little check. Now it's a counting game, which is hard. 1, 2, 3, 4, 5, 8, 9, right, here. 2, 10. Who would guess that 5 times 2 is 10? That's weird. You're 10? Here's the sort of thing that can happen. Suppose I was a really bad drawer and did this. See how they would introduce false intersections? So I guess I have to be kind of neat and make sure that I'm getting the intersections that have to be there. Alright, 5 times 2. I think 6 times 8 is still going to scare me. Hi, welcome. Hi. Come join us if you like. So, all right. So we're playing a game called intersection math. We'll work out 5 times 2, draw 5 dots on one line, 2 dots on another line, connect each dot to every other dot from top to bottom, and then count how many intersections there are. And it turns out that 5 times 2, there are 10 intersections, which doesn't seem weird if you just walked in, but 4 times 3 is 18 intersections. That does seem weird if you just walked in. All right, so let's just do some more examples. I want to see if we can get a feel for it. Give me another small example to do. 3 times 3, go for it. Can you draw a good picture for 3 times 3? Let's see if we all get the same answer this time. Okay, what else are we getting? Just 7? 7? 7, 7? 7? 9? Sorry?
7.
7. Several sevens, yep. 10? 8? Okay, that's a clear answer. 3 times 3.
Oh,
8? Anyone want to revise their answer? Anyone want to revise their answer? Have you got others?
8.
Alright. There is another issue with this one. 3 dots, 3 dots. Okay. So there's 3 lines from each dot from the top. Is that correct?
Correct.
So far, so good. Here's a potential issue. When I connect this line, what happens if I go right through that point there? Because if you're one of those people that did that, you might get a different answer from someone who had a straight line that went just under it. Do you see an issue there?
No, I did.
Yeah. Do you want 3 lines to go to the same point or not? And I'm going to argue the following. So that we're all doing the same thing. Let's assume these dots are spaced, so I'll never have the same intersection point overlapping. Let's get as many intersection points we have to get. So I want all 3 there. And do I remember running the problem again, or think I'm okay? I think I'm okay. So this could be the trouble spot. Maybe you're one of the people that put all the lines on top of each other right in the middle. If you did that, you'll get a different answer than what we're going to get here. Well, by the way, how many sections is that on this board?
Say that again?
How many, what's the answer on the board here? Okay, yeah.
9. 8.
That's 4, that's halfway to 8. 1, 2, 3, 4, that's the other halfway to 8. 9.
And I'm not 7.
Because I bet you went through all 3 here, and what would happen? Would you miss 2 of them? Yeah. So 3 times 3 is 9. Alright, any patterns yet? Or is this just all over the place?
Should do type A. I like that symmetry. And
You
they
like-
have
yeah. I know, I'm breaking that symmetry for you. Yeah. Alright, for those that are type A, do you like how the board looks in general right now? Or do you better, should we neaten up what we're doing on the board? Should we organise this? You don't care? You like it? Alright. So, okay, let's think this way. Are the 1 times tables okay? What's 1 times anything? Do we know that?
0.
Always 0, so that one we know. What about the 2 times tables? So far we've got 2 times 1 is 0, 2 times 2 is 1. Do we have 2 times 3 on the board?
2 times 5.
Oh, 2 times 5 is 10. Well, I know what I want to do. Go for it. Can someone do 2 times 3 and someone else do 2 times 4? Just pick one at random and I trust you this time to get it right. 2 times 3 is 3? Actually, maybe we should get that confirmed. 3? 3, okay. Alright, 3, I'm going to believe you. Okay, what about 2 times 4? Can you use the same diagram? Add another dot to it? Ooh. Like I said, mathematicians are fundamentally lazy. They don't like doing extra work.
Yeah, one more.
6. Yeah.
Is it 6? Did they end up adding 3 more dots? 6? Do you want to do 2 times 6? Do you still have the picture for 2 times 5 anymore, or did I do that on the board? I did that on the board. I erased it. Oh. Might be getting complicated now, might be just too hard to see.
Yeah,
17, 14, okay, it's getting complicated. 17, 14. 15. Alright. 17, 14, 15. Any other answers? Another 15. Oh, you were the 14, but you changed to 15, I think. 2 times 6. 15. Another 15. Should I do it on the board? Is it worth doing that? Yeah? Alright. I don't think I can reuse any of the pictures I have so far. Alright, here goes. 2 times 6. That's 2.
I got 15.
15 is looking pretty good at this point. Alright, here goes. I'll do one dot completely all unto itself, because that seems pretty straightforward. Oh, my lines aren't very straight. Is that okay? So far, so good. Okay, here goes. I'll connect that line. How many intersections so far? None. Then I'm going to connect this one. 1. And I'm going to connect this one.
3.
That gives me up to 3. Connect this one. Adds how many more intersection points? It gives me up to 6. This one.
10.
Because it adds 4.
All the 2's make triangles.
Does that maybe add me 5 more? 2, 3, 4, 5. Is that 15?
Yeah.
15. Okay. Any predictions for what the next 2 times 7 is going to be? Can we just get these 2 times tables sorted out?
21, yeah.
What makes you say 21?
Because the next level will go 6 into 6.
Hang on, one more. What do you mean?
You add 1, then 2.
Oh, up by 1,
Up by 2.
up by 2, up by 3, up by 4, up by 5, up by 6. Now, if I do this, if I really add a 7th dot, here goes. Is that really adding 6 more intersections? Here goes.
1, 2, 3, 4, 5.
New, 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 and new. And plus I'm also going to add that line. Was it adding 6 more?
Yes.
So it really is 21. 2 times 8. That added 6 more, so it adds 7 more. So here goes, here's my 8th dot. Connect up here, no intersections. But if I go over to here, how many of these lines are they crossing? 6.
7.
There's a 7 down here, just what I did. So it really is add another 7?
Yes.
Aha! There'd be structure in those 2 times tables. Alright. 3 times tables. What's 3 times 1? 3 times 2. We must have it on the board. It's the same as 2 times 3 beside, isn't it? Okay. 3. 3 times 3, I remember doing that. That surprised me because it was actually 9. 3 times 4 I know, because that's what I started with, isn't it?
18.
3 times 5, can we do that? I want to know what 3 times 5 is, please. I know. No, I didn't even ask, you just started without me asking.
Three.
30?
Yeah, I go with 32.
32.
No, 30.
30 as well? Or
30
32?
As well.
Someone's
30 as well.
Yeah, some people are getting tired of drawing, so not drawing anymore.
Let's do that.
30? That's confirmed with a picture, is it?
Yeah.
Yeah. 30? Or 24, the other time 30. It's getting a bit unwieldy, isn't it? I'm willing to do it if you want, because I've got 3 times 3 on the board. In fact, not only am I willing to do it, I'm going to do it. Here's 3 times 3. I'm about to make it 3 times 5. Now, I don't think I've spaced my dots well. I might have to do some little bit of fudging with my straight lines. But right now, I need to connect this dot to all 3 at the top. 1, 2, and avoid intersections I've already got. 3. Now comes the scary one. 1, 2. Now I want to avoid the intersections I've already got. I'm going to be a little bit cheaty with my line. Oh, that's pretty good. Is that pretty good?
We'll go with 2.
Alright, that's 9 circled so far, is that right? Ugh, heavens. Alright, 9. 10. Right, there's 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We're up to 20 now. 1, 2, 3. Do you believe me? 4, 5, 6, 7, 8, 9, 10. That gives me up to 30.
That's just 30.
30. I'm not going to make us do it, but you might have a prediction of 3 times 6.
45.
So where's that coming from? Where are these numbers coming from? I don't get it.
That's 3.
Up 3, up 6, up 9, up 12. So you're predicting up 15? Right, we'll say 45. I won't put it down for sure. This is a prediction, so I'll put just a couple of question marks on it. But you're probably right. Okay. 1 times table is done, 2 times table is done, 3 times table is done. All we have to do is get up to the 456 times table. In fact, can I organise that a little more neatly? I'm still getting it. What do you do in like grade 3? What do they put on the walls in the back of classrooms in grade 4 or 3 or something? Don't they have great big tables like this? That's essentially what I'm doing on the right hand side board, aren't I? Okay. 1, 2, 3, 4. How high can I go? Hey, tell me to stop. 456, you're right. Alright, let's work out to our 9 times 9 tables. In fact, it's going to be kind of boring. Why don't we draw these rows?
All the ones are going to be 0.
Oh, I'm just going to do that row. Alright. So, 1 times anything you told me is 0. Zilch, 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 zilch.
Down and then down.
Oh! Zilch, 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 zilch. 2 times 1, we have it, don't we?
Yeah.
Zilch.
That's the 2 times 2.
Oh, take that back. 2 times 1 is zilch. 2 times 1 is... 2 times 2 is...
1.
1. 2 2 times 3?
3.
And 3 times 2? Is that right?
Yes.
2 times 4 is 6, and 4 times 2 is 6?
Yes.
That was it 10 and 10, 15 and 15, 21 and 21, 28 and 28. Oh, what's this one going to be?
We didn't do 9.
I know, what was this? What's in there?
36.
Because it went up 1, up 2, up 3, up 4, up 5, up 6, up 7, 36. Alright, cool. Let's see, what else? 3 times 1, 3 times 1, 3 times 2, 3 times 3 is 9. I do not believe that. 3 times 4 is 18, and 4 times 3 is 18.
I think it's
30, 30. Did we do any others? 3 times 5 we did. Oh, that's 3 times 1. Did we do 3 times 6?
Yes.
Oh, we're guessing 45. That's right, sorry. 45, question mark. This hasn't actually been confirmed. One staring me in the face. Which one do I want to do now? Can you read my mind?
4 times
77.
the one that we get.
No, there's nothing. Yeah, that one's. Doesn't that just call out to you, that space? 4 times 4, that's small numbers. We can actually do that one if we want. Unless you have a prediction for it. Ah, someone has a prediction.
I'll keep a prediction file. Write it down and give it to someone.
Put it in a sealed envelope and mail it to yourself. Until after it's been revealed. 4 times 4.
I want to read it, okay? Is that okay?
That's
28,
29.
29,
27.
27,
I got 27.
27, 3 27s.
I didn't do it, I just predicted.
You're predicting 27.
Yeah.
Okay, 2 27s and a prediction of 27. Plus 28 and 29. Now you actually do it. Okay, please watch me so I don't goof. I know that that's going to be more than 18, because 4 times 3 was 18. There's going to be more intersections than that. 4 dots, correct?
Yes.
Yeah.
4 dots, correct?
I just got 30.
You just got 30, another number, 30. Did I do that dot correctly?
Yes.
Okay, 1 down, 3 more to go. And I don't want to create false intersections by being a bad drawer. Is that correct? Okay, 2 down, 2 to go. That's going to get complicated. 32!
Yeah.
Okay. Then watch me carefully, because obviously this seems to be difficult. I don't want to go through intersections I already have. You see what I have to do there?
Yes.
Is that still basically correct even though the line isn't straight?
Yeah.
Why don't I go there? I should go on here as well.
You didn't
Oh, I did.
Okay, one more for the fourth.
Oh, why don't I do it that way? I'm all over the place.
That's correct.
Alright.
The last one.
Why don't you count them as you go?
I don't know. Why don't I count as I go?
I don't know.
Okay, 1, 2, I'm going to take these ones. Ready? Yes, it's getting messy, I noticed. Yeah, that one's done, that one's done. That one's done, that one's done. Here to here, yes. Here to here, yes. Here to here. And here to here. That one's done. That one's done. I think that one's done. Is that one done? Is that one done? Heavens. Alright, clearly that's more than these sections. Alright, you ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, the answer's more than 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Answer's more than 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The answer's more than 30. Is it 36? 1, 2, 3, 4, 5. In the middle? 36. Is it 37?
36.
36. Four times 5, we didn't do that, did we? Okay. Getting very tiresome to draw these diagrams. Do you have a prediction for 4 times 5? 60? 60? Oh, why 60? Two people just said 60 out of the blue. What made you say 60? Because the other person said it.
It's prize.
Okay, up 6, up 12,
Up 18.
up 18, so you suspect
19.
up 24, so that makes it 60. Oh, I see that.
And also when the 5 goes up 10, up 20, and then up 30.
Up 30? Oh, because this would be 60, wouldn't it? Alright, so these, I can't do question marks. I put little underlines for the ones that haven't actually been confirmed. Do you want to just keep going? What's the next one? What do you predict here? That was up 24, the expect
Up 36.
up 30, let's make it 90.
96. Up 36.
Up 36, so you predict 126. You predict 90, you predict 126.
Not 90, 96.
Wait, and
It
then
will be 90 instead of 90, 96.
6 times 4 would be 96.
60 plus 36 in America is 96.
Oh, is it? That means that 126 is wrong. It's like, good. Alright, then what's this one meant to be?
40, let's see, 134.
Hang on, are you sure? Up 6, up 12, up 18, up 24, up 30 is what we said. That is up 36?
Yeah.
Okay, alright, so that was cool. So it is 90, I mean, am I right, is it 90?
Yeah.
Yes.
I mean, if we believe in the patterns. Alright, what do you predict here?
100, I guess.
Let's see. Up 10, up 20, up 30, up 40, up 50, and this will be 150 as well because it's symmetrical. After this one, 280 here. Okay. And 280 here. This is kind of fun. 6 times 6. So we're doing up 15, up 30, up 45, up 60, so you predict up
75.
Up 75, that makes 225. Then you predict up 90, so it'll be 315. Let's go one more. Up 105 would make that, 6 times 8. If you were going to draw that one, repetitly, you would have seen 420 intersections. Good luck. Alright, so yes, also, goes this way. After 225 comes 315 and 420. Should we just fill in these ones? These seem to be, yeah?
6 times 3, I think it's now 45.
It is 45, you confirm that? Right, I'll take off the little underlines. What comes up to 45? Up 3, up 6, up 9, up 12, up 15. Up 18 would be 63. Up 21. 84. 63, 84, and then let's just fill this one blank here, because this is how I want to. That's right. So the answer is 168? 168. Go with it. All right. Are we ready to answer the original question yet? I know. Why not? I also wonder if these numbers actually are true. What's your guess? Alright, so I have a rule in my life, even when I teach at any level, that every 37.5 minutes, we have a break. We go on for 37.5 minutes. Why 37.5 minutes? Because I once read a paper, years ago, that said in a lecture format, with one person staying at the front of the room lecturing to other people, the average attention span is 37.5 minutes. So I think we should just have a little break for a few minutes, go wander around, come back, and stare at this table, because I want to get up to 456 times 238. Yes, that's good staring. Well done. Alright, so just up and about, just feel free to have a little wander, maybe grab a drink or something. We'll resume in about 4 minutes. Yeah?
I know how to do it.
You know how to do it. Excellent.
I know how to calculate that. But
How would you, okay, tell me, I'm curious.
I don't know exactly.
Okay, but you tell me you've got a good feel for this. You feel like this is within reach. Is that right? Is that right?
Yes.
So you feel like this is doable today?
Yes.
That in itself is great. Alright? And you're actually working on finding it. Okay. What works? What
No,
works?
I'm not looking it up. I'm calculating.
Okay. Alright, so by the way, what's the square root of 9?
3.
Is that true? Is 3 times 3 equal to 9?
Yeah.
Yeah, the square root of 9 is 3. What's the square root of 100?
10, 5.
That's 100. Square root of 100 is 5? Oh. No, apparently 5 times 5 equals 100. What's the square root of 36? 4? Now, what do you notice about these numbers here? Oh, not that one, it's kind of blank. Are they, well, hang on, we're going to be careful. Are they square numbers in ordinary arithmetic?
Yes.
No, in ordinary arithmetic, they're squares. And are they also squares in weird arithmetic?
Yes.
So 36 is normally 6 times 6, but now it's 4 times 4. And 100 is normally 10 times 10, but now it's 5 times 5. Keep staring at that table. In fact, those zeros are distracting. They don't tell us anything when we get rid of the zeros. 6 times 2. Oh, that's a 5. It's 15. Sorry. Welcome to my handwriting.
So you're asking about a pattern on the diagonal?
I'm just wondering if anything's going on that table. I did ask about pattern the diagonals, but I don't know what I'm going for.
Well, that's 3 squared, 6 squared, 10 squared, 15 squared. The next one might be 21 squared.
Oh.
41.
Hang on. 6, do you mean 6 squared here? Or do you mean 6 squared there?
I mean real number on the diagonal.
Okay, this 36 in real numbers 6 times 6. But it's actually 4 times 4 in weird math. But it is 6 times 6 in ordinary math.
Right.
Okay? So where are we going with that?
Well, I'm just looking at real numbers. You've got 3 squared and then 6 squared.
Oh, so this is normally 3 times 3.
Yeah.
This is normally 6 times 6.
Right.
This is normally 10 times 10.
Yes.
This is normally, oh, was that a square number?
15.
Is that normally 15 times 15?
So you had 6 and then you got 21 squared there. Where your finger?
So 441? Is that 21 squared?
Yes.
Yeah.
And the next one should be 28 squared.
28 squared. That's under 900, I can tell you that much. 441, clearly. That's curious. So this 36. But there it is, 6 and 6 squared. 6 times 6 in order arithmetic. Yeah? 784. Okay, well that's interesting. So what if I did this then? All of it's correct. What do you mean by all of it's correct?
3 times 3 was 9, 3 times 6 was 3.
15 times 6, was that in ordinary arithmetic?
90.
What's 6 times 10 in ordinary arithmetic? In fact, if I put a multiplication sign right there, so within the weird intersection math multiplication table sits an ordinary multiplication table. Is that what you're telling me?
Yes.
Wow. Of course, we don't know if that's actually true because most of these numbers are underlined. We just think they're patterns that seem to be true. But we would like that to be true. Yes, I would. I think that's too nice not to be true, but I don't actually know it. All right. Then, if I really want 456 times 238, what could I do? I mean, keep going, all right. But do I need to fill in every single column up to 456?
No.
What would be a nice thing to figure out?
Relations between the intersection multiplication table and the inside.
So what would I need? Will I need this number?
Yes.
I don't know what it is. What else would I need? The number that goes with 238. That number? And then, if this is true, this is ordinary multiplication, what would I do to those numbers? Just do order multiplication on them. Okay. All right. I feel like it's... So what is this? Okay, here goes. This was a 1. That was a 0. So we went up 1, 0 to 1. Up 2, 1 to 3. Up 3, up 4, up 5, up 6, up 7, up 8, up 9, up 10, up 11, up 12, up 13, up 14, up 15, up, whatever that is. Bingo!
455.
Up 455, okay.
Now,
On the previous number.
On the up 455 on the previous number, is that what it is? Okay. What's the previous number?
454.
Oh, up 455. Actually, I do like that approach. I think we've got hope. Because this was 0. This was up 1, gave us 1. This was up 2. So this 3 is really the one we had before, up 2. So what's this 6 really? The 3 we had before, which is 1 plus 2, plus a 3. Alright, then what's this 10 really? What we just had before, plus a 4. This is what we had before, plus 5. So on. In particular, I'm interested in this so on. What's that one? 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. I'm going to cheat. Dot, 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 dot. Plus.
454.
Is it 454, 55, or 456?
55.
Because let's check. This 15, which is the 6th, goes to number 6, was up to 5. 1 less. This 6, which goes to the number 4, so it is 1 less. Looks like it's 1 less. So right now, just believing in patterns. 455. Alright. Alright, what we do is work that one out. Oh, what we're at it, what would this one be? For the 238. 1 plus 2 plus 3 plus 4 plus blah, 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 up to 237. Alright, if I can work out those sums, then all I have to do is work them out and do ordinary multiplication on them, and if everything's actually true, that would be the answer to this. So, okay.
I'm taking that.
Oh, you're taking that now? Okay. Oh, we've got a good 20 minutes, we can wait.
Anybody else want to do it?
Oh, gosh. Oh, what does that mean? Oh, it's a clock. Or a time bomb. Okay, I really want to know what's the sum of all the numbers from 1 up to 455. I really want to know, and I really mean it, because I really want to know, really. Like, really.
Hey, you guys do it too.
Alright, I'm going to ask you, is a mathematician going to want to sit there and add all the numbers one at a time?
No.
No, she's going to want to do something different. There might not be anything different to do, in which case she'll sit there and add them up one at a time.
We can make a
Right, computer programming to do it, that's true.
computer.
That's basically what we're doing. Okay, that's one route, no problem with that.
I've got an idea.
You have an idea? Okay.
You know the story of Gauss?
Never heard of it.
When he was told to add up 1 to 100?
Okay, what did he do?
When he was in 3rd grade?
See, the age changes in different, you know, I've heard the tell when he's 8, when he's 14, when he's
He wrote
15.
the number sequence 2 different ways. You know what I'm talking about?
No idea what you're talking about.
Okay, name one.
Run the sum 2 different ways.
Yeah, 1 forward, 1 backward.
Okay, let me do a small example. And backwards?
And then the 6
Backwards,
plus
okay.
5 plus 4.
We got a
She's
jokes.
in the house.
We got a jokes in here.
Okay.
7
Verticals. I'm hearing 7. Which way do I write 7? This way or this way? Both. 7? That's 7?
Yeah.
7 7, 7, 7, 7. Hey, hang on. I don't know what that's doing for me. Well, I went up to 6. I think I went 100.
42.
Alright, okay. So what does 42 tell me? Agreed, that's 42. So what?
We can fix it and use multiplication instead of adding so much.
Gosh, to solve a multiplication problem, we went to multiplication problem, we got an addition problem, which we're going to solve by doing a multiplication problem. Okay, yes?
Is it 456 to the power of 456?
I do not know.
I mean, it's better.
Alright. Obviously 42 has got something to do with this and this. What's 42 got to do with the two different problems? This seems, I mean, we're doing something. It feels clever, I don't know what it is.
Well, it's taking on the story.
Figure it out. It always adds up to 7 if you take 7 times
It always adds up to 7.
your sum.
What's it? What's it? What's it?
Here it always adds up to
What's
456.
Someone's always saying.
I agree. The sums and the verticals are always 7. What's that doing for me? Because I actually wanted to work out what this is. Is that helping me work out what that is? All it does is just does something that has a pretty pattern to it. Is it a helpful pattern or is it not?
6 times 7 divided by 2.
So it's not like it's 21 and then you multiply by 2.
Okay, you said this equals 21, but my question was, 10 I didn't know it was 21. That would be a question mark, is that right?
Yeah.
What would this be? Would that be the same answer or a different answer? So it would be the same question mark.
Except backwards.
So back. Thank you. If I did this, I get 1 plus 6 is 7, 2 plus 5 is 7, 3 plus 4 is 7, 4 plus 3 is 7, 5 plus 2 is 7, 6 plus 1 is 7 equals question mark plus question mark. That would be
2 questions.
twice the question mark. So this is telling me a whole bunch of 7s equals twice the question mark. But how many 7s are there?
6.
Does it make sense with 6 7s?
Yeah.
Because it came from 6 numbers. This is really 6 7s is twice the question mark. So what was the question mark?
21.
Yeah, 42 equals twice the question mark. So question mark is 6 times 7 divided by 2, which is 21, which is correct. Therefore, I'm interested in this guy. That's the one I really want. 2 of them. That guy and this last. What can I do to this guy here? It equals something questionable. Put a 1. Okay, count backwards. 455. I'm not being Da Vinci anymore. 454. Plus 3 plus 2 plus 1. Will that be the same question mark?
Yes.
Yeah.
So what?
I don't think it was divided by 2.
All right.
Well, you get 456.
How many 456s will I get?
450. 450.
450? Really? 455?
455.
There are 455 456s?
Yes.
455 groups of 456 is twice the answer I want. So the answer I want is 456 times, 455 divided by 2. Oh, I guess you're doing the calculator. Do you want to use a calculator for that? Okay. Can you just read the digits because I can't have a hard time understanding. 103 740. 103 740. Do we trust that?
Yeah.
Alright.
I have the other one.
Oh, the other one. Sorry. Right, the other one. Okay, 237 plus 236 plus 3 plus 2 plus 1. This equals something questionable. Can I do Q for question? Q for question. 237 groups of 238 would be twice the question. Gives me some grand number. 28203. Oh my gosh! That number goes here. This number goes here. Therefore, according to our theory, in intersection math, 456 times 238 would be, what are the numbers again? I can't read. What's that number over there?
203.
Can I read the 103 one first?
103, 740.
740 times, that's ordinary times.
28203.
28203, and I believe there is a way in the calculator, because I'm too lazy to do that by hand.
It's too long.
No, it's not.
Okay, calculator, handle it.
Yes.
2 billion.
2,925,925,779
925 779 220. Okay, in America, you just said 2 billion.
2,900,000.
Okay, that's what a billion is. That's actually interesting. A billion in America is what number? 1,000 million. A billion in Australia is,
Doesn't exist.
it's a million. I'd rather be a billionaire
In
in
Australia.
Australia than a billionaire in America. But look at that! 2 billion US billions, 2.9 billion intersection points.
Wow.
If you were to draw a picture on a big sheet of paper of one line with 456 dots, another line with 238 dots, connect each dot to every other dot, according to our theory, that's how many intersection points you'll see. If that all been really cool, if your school has at least 700 kids in it, line 456 kids up on one side of a football field, line 238 kids on the other side, and everyone holds strings to each and every other person. And they get an aeroplane to fly over and take a photograph. And you should come up, according to our theory, with that many intersection points. Alright. Optional homework. Draw it. What does the word optional mean? Don't do it. That means don't do it. Alright. Okay, so that's brilliant. You worked it out. And that was less than an hour and a half. So my trouble is it actually true?
Yes.
This was just relying on patterns. We never actually checked whether 4 times 5 really was 60. Is there any reason to believe these patterns are actually true? We just went with the patterns. I haven't actually asked whether they're actually true. Yeah?
6 times 10 equals 60, 6 times 15 equals 90.
It fits. Everything's fitting beautifully. But how do you know this pattern of fitting beautifully is actually true? I don't know how a calculator does 7 times 6 in intersection math and really checks whether it really is 3 to 15. That would be a cool calculator. See, the thing is, we haven't even discussed whether any of this is actually true. Except the 2 times tables. I think I remember we kept adding this extra line, and we saw that you would get the next number of dots coming up. So I actually kind of believe the 2 times table. I'm comfortable with that, I'm comfortable with the 2 times column. But we never actually explained that what we're seeing with the 3 times table really was true. Some people just like to believe in patterns and be done with it.
45.
And you did a 45, it was 63 and 84. I believe it's pretty darn compelling, but I would be shocked if it's not true.
Why would it write down big numbers?
I don't know. Why would it hold true with big numbers?
Why not?
Why not? Like I said, we don't know. breaks down with big numbers or doesn't break down with big numbers. Trouble is, I don't actually know which. Well, see, that's where you're getting a mathematician. Mathematicians tend not to believe things because they see it look good. Unless I can figure out the logic behind it. So, here's other optional homework. Is this actually true?
Yeah.
Obviously, I don't want to do all of them because I'd have to do all of them up to this number, which I didn't want to do to begin with.
Well, the second option is easier than the first one.
That's true. I think trying to figure out what's logically valid or invalid behind this might be easier than drawing that. I'm with you.
Did you make that up reference? Did you have that?
No, I made that up. No. I didn't know what the answer was until now. It's kind of cool to know the answer 2.9 billion.
Is there an easier way to do this, man?
I don't know.
Intersection man?
Is any of this actually true? Welcome to my world. Play with stuff, get excited by stuff, but then you have to ask yourself in the end, well, that's well and good, but is it actually true? And of course, mathematicians make things worse. Shall I make things even worse for us right now?
No.
I heard a yes just there. Yes. Who said intersections? Let me draw.
Three-dimensional.
Oh, now you're thinking like a mathematician. Let's do 2 times 4. Should we fairly easy one? What is 2 times 4? Is it easy? 2 times 4 is 6. Should we just 6 intersections? Not too bad. 1, 2, 3, 4. See, now you're really thinking like mathematicians. This is great. Okay, so I did intersection math, and that was counting intersections. How many lines did I just draw? So 2 times 4 in intersection math was it said 6? 2 times 4 in line math. Was that 8 lines? And 2 times 4 in space math. What do you think I mean by space? No, I mean that picture. What do you mean by space?
Oh, how many spaces are
How many spaces? How many spaces do you see? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Do you count those as space or not?
No.
Okay, we'll count those as space.
No.
We'll count those as space.
No.
We'll count those as space. Alright, I'm with you. 13?
Yes.
Oh, look at that. 2 times 4 is 13. Space math.
So these are actually line segments, like the little segments.
Or you do, okay, 2 times 4 in little segment math. What's 2 times 4 in little segment math? Okay. 1, 2, 3, 4, 5, 6, 7, 8. Am I doing it correctly? 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Did I?
20.
In the very middle.
20?
Yeah.
How about angles?
Alright.
Are these all real math?
They are now, we've made them up. That's the thing about math, you can make it up, it's creative, it's yours, do whatever you want with it. Do you know what? I have never thought about angle math. That's new to me. How do you want to measure angles? It's your math. How do you want to do it?
Get a big protractor.
Oh, actual angles?
Oh.
I do have one trouble with that. Because we can put this dot anywhere we want, the angles will change. Do you want to just count how many angles there are?
Yeah.
Do you want to count that as an angle? I mean, there's choices. It's your math. Do you want to count that as an angle? It's your math.
No.
No.
No, alright. Just something like that?
Yeah.
Inside.
1, 2, 3, 4, 5,
No,
6.
not that. Not that one on the top. Yeah, that one on the
I know it's your math, so I'll do whatever you want.
Yeah.
It's in there.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And all these things in here? 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 40, 41.
41.
A good prime number.
You know, what are these? 40.
Oh no, this one.
Yeah, 42 because it counts 40 twice. You said 40, 40, 40.
It's because it's already marked, I think you got it.
Oh no.
42.
See, I'm cooking with. Alright, so it seems to me you have a lifetime of work ahead of you. And I also like 3 dimensions.
Oh, yeah.
There must be a 3-dimensional version of all this you can play with.
Okay, come on, we're going to text from right now.
Alright, so
Come up to the,
it seems that the organisers have produced something that I've produced that gives many of the answers away. Do you want the 6 document or do you not want the 6 document?
No.
How big is it? It's only this big.
yeah.
How big are pages?
You want it?
What is it?
Well, it explains everything I know about intersection math and a little bit more, but not about stuff you've invented.
That's all I need.
Did you want one?
Is it talk about
The application of it, or is it?
Applications?
Yeah,
What's the point? What's the point of playing the violin?
Oh, that's a good point.
Ah! Anyone else like one?
Yeah, one.
Okay.
I've got this.
Got his?
Is that you? Is that you, James?
I'm James. Oh, I'm Jim. I'm Jim and James. I'm James Ham. And if you want to write to me, that website, my website has my email address, because I'd be very interested if you did actually do this one. That's brand new to me. Because I bet there's probably some good math in that one that I've never thought of. You guys could discover. And I bet you're probably the very first people on the planet to ever think we could play with that. So that would be your math for sure. That'd be way cool.
Is there any history to all this? Like the one you go?